Good afternoon. Welcome to the OSIRIS-REx Approach Campaign Media Telecon. I'm Nancy Neal-Jones from the Office of Communications at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Graphics for today's telecon can be found at www.nasa.gov/live. We will take questions from media and social media at the end of the presentation. Use hashtag AskNASA to ask questions on Twitter. We're here today to get an update on OSIRIS-REx, NASA's first asteroid sample return mission. Since its launch on September 8, 2016, the spacecraft has been en route to rendezvous with its target, asteroid Bennu. In the first video, the spacecraft is shown during its approach phase of Bennu. Approach phase began on August 17th and continues until the spacecraft arrives at Bennu on December 3rd. The primary goals of approach are to visually locate Bennu for the first time, survey the surrounding area for potential hazards, and collect enough imagery of Bennu for scientists to generate a detailed shape model of the asteroid, assign a coordinate system, and understand its spin state. Now we'll turn to the panelists to tell us about mission activities. We have with us today Lori Glaze, Acting Director of the Planetary Science Division at NASA headquarters, Dante Loretta, OSIRIS-REx Principal Investigator at the University of Arizona, Tucson, Michael Moreau, OSIRIS-REx Flight Dynamics Systems Manager at NASA's Goddard Space Flight Center, and Sandy Friend, OSIRIS-REx Mission Support Area Manager at Lockheed Martin Space. I will now turn it over to Lori Glaze. Lori, take it away.
Thanks a bunch, Nancy. This is a really exciting time for planetary science. NASA has an incredible fleet of missions that are in formulation, implementation, or operations that you can see on my first chart. In addition to OSIRIS-REx, which is shown on the far left here, other planetary missions with major upcoming milestones in the coming months include InSight, which is shown in the inset, the Mars inset at the bottom right, which will be landing on Mars in late November, and the New Horizons mission, shown at the top right of the chart, which will execute the first flyby of a Kuiper Belt object on January 1st. Several of the missions in our fleet here have been competitively selected through NASA's New Frontiers program that you can see on my second chart. The New Frontiers program is a program that solicits mission concepts about twice a decade, with each mission costing about $1 billion. So far, NASA's flown 3 New Frontiers missions, including New Horizons, which flew by Pluto in July 2015 and is now, as I said, on its extended mission to fly by a Kuiper Belt object. Juno, which has been probing the structure and composition of Jupiter's atmosphere for just over 2 years, and of course, OSIRIS-REx, which we'll be talking about today. I also wanted to mention that NASA is currently in the process of conducting 2 Phase A studies to determine the next New Frontiers mission. The 2 missions that are currently in competition are CAESAR, which is a comet sample return mission, and Dragonfly, which is a mission to explore Saturn's moon Titan. If you were looking closely at the planetary mission fleet, you would have seen that several of the missions in our fleet are focused on answering important questions through missions to asteroids or small bodies in our solar system. My third chart shows some of the high-priority science questions that we're interested in trying to address through missions to small bodies. These include understanding the formation and evolution of our solar system and the role that the small bodies play in delivering water and organics to the planets. Other major science themes include understanding processes that are active in our solar system, resources that might be present, and finally, understanding the hazards that these small bodies may pose to life on Earth. Each of our missions that are shown in this chart here is focused on a different set of questions and lives in a different part of this kind of question land. OSIRIS-REx is visiting and sampling a near-Earth asteroid that is probably rich in organics. It will address how Earth acquired its water and organic matter and help us better understand the potential hazards of asteroid impact. Laboratory analysis of the Bennu sample when it gets back to Earth will give us clues as to how these objects formed and what resources they may hold. And with that, I'd like to hand things over to the OSIRIS-REx PI, Dr. Dante Loretta of University of Arizona, to give us more details about the OSIRIS-REx mission.
Thank you, Lori, and thank you to all participants in today's Media Telecon. This is a very exciting time for OSIRIS-REx. I want to start out with a little bit of background information on the mission. On my first chart, I've got the awesome acronym that spells out our mission name, which captures the principal scientific objectives of OSIRIS-REx. First and foremost, we are an origins mission. We are seeking to return samples of a carbonaceous asteroid that we believe dates back to the formation of our solar system and holds clues to not only to the prebiotic molecules that may have led to the origin of life, but in general to the delivery of volatiles like water that made Earth a habitable planet and can help us understand possible distribution of life throughout the solar system. We're very interested in the spectral properties of our target asteroid and indeed of asteroids across the solar system. There's over 700,000 known asteroids, and we are not going to be able to send a spacecraft to all of them anytime soon, unfortunately. Most of them will only be characterized using telescopic instrumentation, and when we study the spectroscopy, we're looking at how sunlight is reflected off their surface or how energy is emitted from the surface. And OSIRIS-REx provides the opportunity to ground truth that spectral information and help us interpret the composition of these asteroids across the solar system. We are also a resource identification mission. We are going to a near-Earth asteroid that's in a very Earth-like orbit. We chose it, one of the reasons was because it's accessible. We can launch a spacecraft from the Earth, rendezvous, collect a sample, and bring it back. And that's the kind of object that would be of interest for any resource development. And we're developing the technologies and capabilities to survey these objects, perform precise navigation, as you'll hear from my colleague Mike Moreau, and further that objective to enhance human and robotic exploration across the solar system. We're very interested in the security aspect of these asteroids as well. Bennu is designated as a potentially hazardous asteroid. It has a not insignificant probability of impacting the Earth. The good news is that impact would be well into the 22nd century, so it's not something we worry about right now. But we do want to understand this object, and most importantly for OSIRIS-REx, we want to understand all of the forces that influence its orbital trajectory. In particular, there's a phenomenon called the Yarkovsky effect, which is related to how the absorption of sunlight and the emission of heat from the asteroid's surface can substantially change its orbital trajectory. And we must account for this force if we're going to be able to predict where Bennu is going to be in the future and the likelihood that it's going to impact the Earth. And then finally, we are a regolith explorer. Regolith is what we call the loose gravel and soil on the surface of an asteroid and other airless bodies. And we are going to be bringing that material back to the Earth for detailed analysis in our laboratories. On my second chart, I've got an overview of the science deck of the OSIRIS-REx spacecraft, just to orient you to all the different sensors that we have and the information we're going to be collecting over the next several months. First of all, I want to draw your attention to the three camera systems that are called out here, the Polycam, the MapCam, and the SamCam. Combined, these sensors make up the OSIRIS-REx camera suite, or the OCAMS system. This was provided by the University of Arizona, and in fact, it was the Polycam that was the sensor that picked up the first images of Bennu on August 17th. We also have our visible and infrared spectrometer on the lower left. We call that OSIRIS. That was provided by the Goddard Space Flight Center. It's a point spectrometer that covers the wavelength ranges from 0.4 to 4.3 microns, which gets us key information about the reflectivity of the asteroid's surface, the possible presence of organics and water-bearing material, and identification of other mineral species. Our thermal emission spectrometer is OTIS, provided by Arizona State University. This is measuring the heat flux off the surface of the asteroid, which is important for assessing the surface for spacecraft safety, as well as understanding the influence of thermal emission on that Yarkovsky effect that I mentioned, and there'll be mineral identification information in that data as well. Over on the right, we have the laser altimeter OLA, provided by the Canadian Space Agency. This is a two-axis scanning LiDAR that's capable of determining the range between the spacecraft and the asteroid surface from 7 kilometers down to hundreds of meters. And we'll be using this instrument to build up topographic maps of the surface and the detailed shape model. And then finally, in the upper left, we're very proud of our student collaboration experiment, the Regolith X-ray Imaging Spectrometer, or REXIS, built by a team of students at the Massachusetts Institute of Technology and Harvard College Observatory. and that is going to be looking at X-ray emission from the surface and telling us about the chemical elements like iron and silicon and magnesium and their distribution across the asteroid surface. And now I know you all have been anxious to see the first image of Bennu that is in my third chart here. I can't explain enough how much it meant to this team. I know Bennu is only a point of light here, but many of us have been working for years and years and years to get this first image down, and it really represents the beginning of the great scientific expedition that is OSIRIS-REx. This image was taken on August 17th at 6:35 a.m. UTC. We were at a distance, and I'll be very specific here because it's important, of 2,186,228 kilometers. That's significant not only because that's when we could detect the asteroid, but it's also the closest we have ever been to Bennu. Asteroid Bennu was discovered in September of 1999 at a distance of over 2.2 million kilometers. So this was significant in that we are now in the vicinity of the asteroid, closer than we have ever been, even during the close approaches of the asteroid to the Earth. This is a series of 5 images that was taken over the course of about an hour, and we did that so we could see the asteroid moving against the background star field. So if you're looking at the video or the animated GIF, you can see the green circle indicating asteroid Bennu as it's on its orbit. There was a lot of good news in this image for us. First of all, the asteroid was right where we thought it was, so it's there and it's waiting for us. The spacecraft was also where it was supposed to be and pointing in the direction, so our spacecraft navigation team has done a fantastic job so far getting us on this approach trajectory to Bennu, and the spacecraft has operated flawlessly throughout the outbound cruise phase, and its ability to point the cameras and to collect this important data has been well demonstrated here. You'll hear more about the spacecraft from Sandy Friend from Lockheed Martin later in the presentation. The asteroid was also at the brightness that we expected it to be, which is right around 13th magnitude. The other stars, kind of that triangle of stars just above it and to the right and left of Bennu, those are all around 13th magnitude as well. You can't see those stars from the Earth with the naked eye, but Bennu was as bright as we anticipated it to be, which is good news because a lot of our camera operations, exposure times, etc., are based on our knowledge of the reflectivity of the asteroid surface, and so far there's no surprises there. And finally, even though we'll be doing a more detailed survey of the asteroid environment later on in the approach phase, we were able to process the images to see if there was any extended material around it that might indicate a recent impact or a comet-like dust outgassing event. There's no indication of any material in the vicinity of the asteroid. So far, so good for proceeding with our nominal approach phase trajectory. But we will be doing more surveys of the asteroid environment. That's one of the key objectives of the approach phase. And then just to give you a better sense of what's happening over the course of the OSIRIS-REx mission, on my fourth chart, I have an overview of the entire asteroid proximity operations plan. I want to draw your attention first to the campaigns that are called out in the middle of that bar, starting with the navigation campaign, which is what we entered into with the beginning of the approach phase. We're then moving on to the real science campaign. We call that the site selection campaign, where we'll do global mapping, ultimately selecting regions of interest on the surface for detailed reconnaissance. And then the mission will culminate at the end of 2019 and into 2020 with the sample acquisition campaign, where we begin the process of rehearsing the very close approach to the asteroid surface, ultimately committing the vehicle to about a 5-second contact to collect our sample in what we call our touch and go or tag sampling event. On my next chart, chart 5, I have details of the navigation campaign and some highlights of what's going to be occurring over the next several months. So as I indicated, the approach phase began on August 17th. That was when we were able to detect Bennu and provide those images that I just presented. The next science activity occurs on September 11th and 12th, where we have a dedicated dust plume search campaign. We have no indication that there is dust in the environment of the asteroid from our extensive ground-based astronomical campaign, but we do want to make sure it is safe for the spacecraft to enter the asteroid vicinity, so we'll be doing this survey just to ensure that our assessment from the ground-based information is correct. I should have mentioned between now and then we are doing regular optical navigation imaging, and Mike Moreau will talk to you more about how his navigation team uses that information to determine the spacecraft trajectory and design their approach maneuvers, which are indicated on the upper part of the diagram starting on October 1st and running through November 12th. We will be performing some TAG-SAM testing. TAG-SAM is the sample acquisition mechanism. It's been in a launch configuration ever since September 8, 2016, when we left the Earth. And Sandy Frund will tell you about the plans for Lockheed Martin to deploy the launch cover and extend the arm and exercise that system. Then in October, starting on October 23rd, we'll be looking for any natural satellites that may be in orbit around Bennu. Again, we have no evidence that these exist from our ground-based astronomical campaign, but we are looking for objects as small as 10 centimeters, and we would not have been able to detect those from the Earth or from our space-based telescopes. So we'll have a whole campaign to see if there's anything in orbit around the asteroid. And then finally, right at the end of the approach phase, beginning on November 12th, when our last asteroid approach maneuver executes, we'll be having detailed, higher resolution imaging, ultimately building up a shape model of the asteroid with a scale of about 75 centimeters per facet. So that'll be a very important product both for the navigation team, also for science. We use that to understand the nature of the surface, the geology of the asteroid, and we use that as the framework upon which we overlay all the other mapping information. Then we move into the preliminary survey phase. We'll perform a series of hyperbolic flybys over the poles and the equator of the asteroid, permitting us to measure the asteroid mass, get higher resolution imaging, and really set the navigation team up for their orbital insertion and the beginning of the orbital A phase. So with that, I will pass it over to my colleague, Mike Moreau, who will tell you about the navigation team, the amazing work that they've done to get the spacecraft to this point, and what we're going to be up against as we begin the proximity operations phase of OSIRIS-REx. Over to you, Mike.
Thank you, Dante. So in my job, I lead the team of engineers from Kinetics Aerospace and Goddard Space Flight Center that comprise the navigation team for OSIRIS-REx. And I'm going to tell you a little bit about some of our preparations to navigate the spacecraft in close proximity to Bennu and some of the challenges that we're going to be facing. So the first graphic that I'm going to talk to starts with an animation of the spacecraft around the time of the Earth gravity assist. This activity happened in September of 2017. So since launch, OSIRIS-REx has conducted a series of maneuvers in conjunction with this Earth flyby to target the arrival at Bennu this fall. And so when we flew by the Earth, the flyby changed the plane of our trajectory to align us with Bennu's orbit. And then in July of 2018, we performed another correction to our trajectory that precisely targeted our arrival at a point 175,000 kilometers, or about 110,000 miles from Bennu on October 1st. So we're targeting this point on October 1st, and on that date, and then again on October 15th, we plan to use the main engine thrusters on the spacecraft to slow our approach with respect to Bennu. There are two asteroid approach maneuvers called AAM-1 and AAM-2 that are going to slow our velocity from nearly 500 meters per second to approximately 5 meters per second. So right now, we are closing with approximately 1,100 miles per hour, and that will be slowed down to about 11 miles per hour after the AAM-2 maneuver. So following that, the spacecraft will conduct a series of weekly maneuvers that are targeted to fly us through a precise corridor during our slow approach to Bennu. And this corridor has been specified by the scientists in order to conduct a series of observations and characterizations of the environment around Bennu, as Dante referred to earlier. Ultimately, our last approach maneuver, AAM-4, on November 12th, will adjust our approach to target arrival at a position that's 20 kilometers away from Bennu on December 3rd. This event will signify our official rendezvous with Bennu and the commencement of proximity operations, as illustrated at the end of this video. So my second graphic kind of talks about this first phase of proximity operations and shows you the path that the trajectory will follow. So we'll be conducting a series of close flybys of Bennu that will be conducted between December 3rd and December 17th. These flybys are going to take the OSIRIS-REx spacecraft within 7 kilometers of the surface of Bennu. This will be one of the most challenging phases in the early part of the mission for both the navigation operations team. These maneuvers are designed to collect observations of Bennu, but also to sense the gravitational pull and allow us to derive the mass of Bennu. To accomplish this series of flybys that are being shown on the screen right now, the navigation team has designed a series of maneuvers that will be executed every 48 hours to target multiple waypoints in the vicinity of Bennu and execute these these precise flybys of the North Pole, equator, and South Pole of Bennu. Following the last flyby of Bennu, the OSIRIS-REx spacecraft will drift away for a few days and then use a series of 3 maneuvers to insert into orbit around Bennu for the very first time. So my third graphic illustrates the relative sizes of some of the asteroids and comets that have been previously visited by spacecraft. We wanted to highlight Bennu's size because it's Bennu's size and small mass that make the navigation challenges on this mission unprecedented, really. So Bennu is about 500 meters in diameter. It's one of the smallest objects ever to be visited by a spacecraft. And on December 31st, when we insert into orbit, Bennu will become the smallest planetary object to ever be orbited by a spacecraft. So it's Bennu's small size and mass that are really making this mission very challenging and exciting from a navigation perspective. To give you a little bit more perspective on this, when the OSIRIS-REx spacecraft is in this first orbit, it will be approximately 1.5 to 2 kilometers away from the surface. As a point of comparison, many of you are, I'm sure, used to flying across the country in a commercial airliner. You look out the window, you're about 10 kilometers or 35,000 feet above the ground. So imagine looking out the window and being 10 times closer to the ground. That's the distance that the OSIRIS-REx spacecraft will be from the surface of Bennu. And in this orbit, another fact for you, the orbital velocity of OSIRIS-REx about Bennu will be about 5 centimeters per second, or 0.1 miles per hour. So why are these speeds so slow, and why are we so close to Bennu's surface? It's because the object is so small. So it's very exciting to be involved in doing something really new like this. So before I end, I wanted to talk a little bit about the techniques we're using within the navigation team to accomplish the mission. And during this whole period I've been talking about, we will use radio tracking data that is derived from our radio signals between the spacecraft and the Deep Space Network stations back on Earth. But we've also begun now to use optical navigation images of Bennu to determine the position of the spacecraft over time. So Dante showed the first images that were recorded on August 17th. We also recorded our first optical navigation images using Polycam on that day. And since then, we have been conducting OpNav imaging at a regular cadence of 3 times a week. And so my last graphic highlights 3 different optical navigation techniques that will be employed as the mission progresses. So currently in the images that you saw, Bennu appears as an unresolved point of light. And it's the relative motion of Bennu with respect to the background of stars that's utilized as a navigation measurement. This situation is illustrated in the left pane of the graphic. In mid-October timeframe, as we move closer to Bennu, Bennu will become resolved, spanning multiple pixels and then a large portion of the field of view in these optical navigation images. This situation is shown in the center pane. And so in order to use these images for navigation, our optical navigation engineers from Kinetics will first have to solve precisely for where the location of Bennu's center is, and then determine that location of the center with respect to the background stars. So in the last image on the right side of the graphic shows the situation when we will begin using landmarks or features on the surface of Bennu as our navigation aid. So once we get into orbit around Bennu, the asteroid will fill a large portion of the field of view of our wide-angle navigation camera. And we will transition from using stars as our primary reference to these landmarks on the surface. And so this technique requires the development of topographic maps and shape models, as Dante referred to in his remarks. Those will be developed from the images that we collect during approach and preliminary survey, and the navigation team will begin navigating using images of Bennu and correlating against these maps to serve as our navigation source. So our entire navigation team is extremely excited to begin putting some of the extensive plans that we've been working on into practice and navigating in close proximity to Bennu. and commencing this exploration of this object to see what surprises are in store for us. So with that, I wanted to hand it off to our final speaker, Sandy Friend from Lockheed Martin. Sandy leads our exceptional spacecraft operations team at Lockheed Martin, and she'll be talking to you about the status of the spacecraft and some of its capabilities. Over to you, Sandy.
All right, thank you, Mike. I'm really excited to be here as we celebrate this historic milestone of taking the first image of Bennu with OSIRIS-REx. Do you want to talk a little bit about our role here in this mission? LM Space did design and tested OSIRIS-REx. You can see in my first image a picture of the spacecraft in the clean room. Featured in this image is the payload deck and all of the instruments that Dante described. In the center of the payload deck, you'll see the sample return capsule, which is responsible for bringing those samples of Bennu back in 2023. Also, on the left side of the spacecraft, you'll see our high-gain antenna. We are now performing mission operations for the OSIRIS-REx team. What that means is that we work very closely with the navigation team, designing and implementing all of the activities and maneuvers that Mike just described. We also work very closely with the science team at the University of Arizona to integrate all science and spacecraft activities. Once all activities are turned into spacecraft commands, they are then packaged and sent to OSIRIS-REx from our facility here in Littleton, Colorado. The spacecraft is performing as expected. All of our cruise checkouts and cruise activities are complete. The spacecraft is ready to support proximity operations, and the mission support area team here is excited and also ready. As we look towards arrival, we have many new and innovative activities that the team is looking forward to supporting. As Mike mentioned, this will be the first time we will support close proximity operations around a small planetary body. Our team will support the navigation team in the precision flying required for the success of this mission, and we will provide support for all of the science activities and observations. Based on our ground testing, we estimate up to 50 command packages will be sent each week, which translates into approximately 30,000 commands executing onboard the spacecraft every week during the peak of proximity operations. Before we get there, though, our mission support area will continue a decade-plus test program of the touch-and-go sample acquisition mechanism, which we call TAG-SAM. This will make sure that we are ready to collect samples from Bennu's surface. My second image shows ground testing of this component. In this image, you can see the arm and the sampler head in our clean room during assembly and test operations. TAG-SAM was invented and developed by Lockheed Martin and uses compressed gas to stir up regolith, the asteroid surface material from Bennu. It is then collected into a special ring-shaped canister that looks something like the air filter on your car, also shown in this image. My third slide is a video showing some of our ground testing of the arm integrated with the spacecraft. In this video, you can see the test removal of the launch cover. That cover is there to protect the TAG-SAM head from contamination during launch and cruise phase. You'll also see the arm move slowly through a series of motions. This arm is a lot like a human arm in that it has a shoulder, an elbow, and a wrist. When it is fully extended, it is approximately 11 feet long. It moves in a single plane to keep the design simple and to maintain tight alignment across the range of motion. As Dante alluded to, later this year we will deploy that launch cover and we will move the arm through a series of motions, taking several images. This will ensure proper functioning and ensure that we are ready to collect those samples in 2020. My last graphic shows an animation of what that operation will look like in flight. It is an honor for all of us here at Lockheed Martin in the mission support area to support this history-making mission. The team is very excited, and we are looking forward to learning even more about Bennu with the amazing team across the country and the world. I will now hand this back to Nancy for questions.
Okay, thank you, Sandy. So, operator, we're now ready to take media questions.
Thank you. We will now begin our question and answer session. If you'd like to ask a question, please press *1. Please unmute your phone and record your name slowly and clearly when prompted. Your name is required to introduce your question. Again, that is star 1. Our first question comes from Mike Wall with space.com. Your line is open.
Thank you guys for all doing this. I just had a quick question about dates. Could you clarify when the actual asteroid arrival is? Because, I thought I remembered it was December 3rd, but then I heard somebody say December 31st, or, did I hear that wrong? Could somebody clear up when asteroid arrival will actually happen?
Sure. This is Dante Loretta. I'll take the first stab at that. So December 3rd is when we transition from the approach phase into the preliminary survey phase. So there'll be a maneuver that sets up the trajectory that takes us over the north pole of the asteroid, and that's what we have defined as our arrival. We'll do a close approach about 7 kilometers over the surface, and then we'll repeat that 5 different times, 3 times over the north pole, once over the equator, and once over the south pole. That is providing the mass of the asteroid and giving us an assessment of the gravity field, which Mike and his team need in order to design the orbit insertion, and orbit insertion is anticipated for December 31st.
Great, thank you.
Thank you. Our next question comes from Bill Harwood with CBS News. Your line is open.
Thank you. Dante, if you see a dust plume or anything around Bennu, what are your options then if you see something like that? And I'm sure you've already told us this before, but are there any options for retargeting a different body if this one proves untenable, which obviously no one thinks it will be, but just in case?
Great question, thank you. And Mike may want to weigh in on this as well. So we do have contingency plans on the shelf for both a dust plume detection and a natural satellite detection. And if we feel that there is a hazard in the asteroid environment and it is not safe to commit the spacecraft to the preliminary survey phase, we will execute those contingency plans. Primarily, a braking burn will occur, which will slow the spacecraft's approach, and we will not enter into the vicinity of the asteroid. Instead, we will then modify our observation plans to better characterize the phenomenon, be it dust plumes, periodic plumes, or a dust cloud, or a natural satellite, make a thorough safety assessment, and then decide how we're going to proceed to enter into the vicinity of the asteroid. Mike, do you want to maybe talk a little bit more about what your plan is from the navigation side?
Well, Dante, I think you covered it really well. We've thought about these contingencies, and basically what it means for the navigation team is we pause, and then we can either decide it's safe to proceed along the trajectory that we've previously designed, or we pull one of these contingency plans off the shelf and we start looking at modifications to those trajectory designs to achieve, the observations that we still wanted to, but to avoid this hazard. So that's one of the things we're most eager to learn over the next couple of months is what Bennu is going to throw us in terms of curveballs, and are we ready for all those possibilities? So.
And Bill, I'm sorry I didn't answer the second part of your question. We are committed to Bennu. There is no option to go to another asteroid and attempt to sample.
Okay, thanks.
Thank you. Our next question comes from Travis Gailey with the CBS News. Your line is open.
Really, to any of your knowledge, is this the most imminent or closest asteroid that is coming or heading toward Earth?
This is Dante. I'll answer that one as well. So Bennu is identified as a potentially hazardous asteroid, and it is one of the top potentially hazardous asteroid with a 1 in 2,700 chance of impacting the Earth, again, late in the 22nd century, so a long time from now. And it is kind of trades for the top spot. It depends on the timeline that you want to integrate it over. I believe 1950 DA is identified as the most potentially hazardous asteroid. But Bennu is one of the ones that we are watching, that as maybe Lori wants to talk about the Planetary Defense Coordination Office at headquarters and how they're assessing the overall asteroid impact hazard.
Yeah, thanks, Dante. Absolutely true. There's an organization here at NASA headquarters called the Planetary Defense Coordination Office that the primary focus is on trying to better characterize and understand potential threats from asteroids and other near-Earth objects in the solar system. It's actually an effort that's working in coordination with other federal agencies to prepare us for potential impacts, and That program actually involves a whole network of ground-based telescopes and space-based assets to identify potential threats and to characterize those threats. And so there's an ongoing program to continuously be scanning the skies and looking for new objects that could potentially pose a threat in the future. Did that answer your question?
Sorry, yes, that's great. Thank you.
Mm-hmm.
Thank you. Our next question comes from Marcia Dunn with the Associated Press. Your line is open.
Yes, thank you. When you actually go into orbit on New Year's Eve, how long will it take you to do one orbit of Bennu if you're only a couple kilometers above the surface? And when you're doing the flybys, are you sort of just flying in tandem with Bennu at that point, or does the spacecraft have to do a lot of back and forth maneuvering?
Sure, I can try to take that question. This is Mike Moreau. So for the first question, once we get into orbit, the period of our orbit or the time it takes to do one full orbit is actually somewhat uncertain because our idea of what the mass of Bennu is very uncertain. But I believe we're looking at an initial orbit that's somewhere between 24 and 48 hours in period. So it will take 1 to 2 days approximately for Bennu to orbit, for OSIRIS-REx to orbit Bennu during this period of time. And then to address your second question, because the gravitational pull of Bennu is so small, we are essentially formation flying around Bennu. So I mentioned during the preliminary survey phase, we're doing flybys essentially every 2 days. And in order to conduct those flybys, we need to do maneuvers that essentially put us in a completely different direction. So we will fly by the North Pole, we'll do a right turn, head down to the equator, then we'll fly over the equator. 2 days later, we'll do a right turn and fly over the South Pole. So we'll repeat this cadence throughout the mission with maneuvers conducted anywhere from 2 to 4 times per week in order to execute the science observations that have been planned by the team.
Thank you. And, there'll be New Horizons arriving to the Kuiper Belt object on New Year's Eve, too. How's NASA going to juggle all this? I'm just wondering there for headlines, it's going to be a pretty crazy day.
I'll take that one. Yes, this is Lori, and it will be a crazy day. The whole fall, as I say, is going to be pretty cram-packed with exciting planetary events, with InSight landing on the surface of Mars, OSIRIS-REx arriving at Bennu, and then going into orbit at the end of the month, and as you say, New Horizons actually executing the flyby of MU-69 Ultima Thule on January 1st. So it'll be a great challenge for all of us to, it'll be the season of science. We will be enjoying every minute of it, and it'll be a great time for all of us, and I hope everyone's ready to stay up all night on the 31st and enjoy the whole package.
Thanks.
Thank you. Our next question comes from Lisa Grossman with Science News. Your line is open.
Hi, thanks for taking my question. Dante, could you just repeat what the closest approach distance was before this, what the closest Earth has been to Bennu before the spacecraft got there? And then also, can you compare this object to Ryugu, which the Hayabusa 2 spacecraft has been exploring this summer too?
Okay, the closest that Bennu has ever been observed from the Earth occurred on September 22nd, 1999, and that's right at the Discovery apparition. And it was 2,204,008 kilometers during its closest approach to the Earth.
Okay.
And could you repeat your second question?
How is Bennu similar to or different from Ryugu, which is the asteroid that the Hayabusa 2 spacecraft is also observing right now? I think they're similar in size, but what else is different?
Right, and we need to actually wait to learn a little bit more about Bennu. We certainly have what we call our design reference asteroid, which is the information that we've inferred from Bennu from our ground-based campaign, but the high-resolution data will allow for a much better comparison. But you're right, Ryugu is much bigger. The mean radius of Ryugu is about twice that of Bennu, and volumetrically, Ryugu is about 6 times the size. So it is a larger class object. The Hayabusa 2 team did not have a shape model based on radar data like we have for Bennu. So we had expected Bennu, we do expect Bennu to be in this spinning top shape. And Ryugu turned out to have that shape. So that was actually good news from my perspective, because that shape, when you process the radar data, you have to worry about the symmetry and the ridge line or that equatorial bulge that's characteristic of the object lies right on that axis of symmetry. But when we saw Ryugu, we said, aha, this is actually a real shape that asteroids take. It's fascinating. It's something that we're learning about as these missions play out. And the best news for OSIRIS-REx is that we designed our observation campaign around that shape, and so that means that work is most likely valid. Both asteroids are very dark. Ryugu has a geometric albedo, which tells you about how much sunlight is reflected off its surface, of between 4 and 5%, and that's the same range that we have estimated for asteroid Bennu. So we believe that they are similar in composition, but of course, they're sample return missions, and part of the science is to really understand what that dark surface and the generally featureless spectral properties mean for the composition of these objects.
All right, thank you.
Thank you. Our next question comes from Brooke Hayes with UPI. Your line is open.
Hi, I was hoping someone could speak a little bit more about the aspect of the mission related to resources on the asteroid, and how that research might play into, future benefits to long deep space missions, and on top of that, whether any private companies have expressed interest in kind of the findings you're going to have for resources on the asteroid. Thanks.
Sure, this is Dante again. I'll take the first crack at that answer. So I have worked with Planetary Resources, so full disclosure, I'm on their scientific advisory board that is a private company that is interested in asteroid mining. So I do have an interest there and a collaboration established with that group. And certainly Bennu rises to the top of the list as potential resource targets when commercial entities like that take a look at objects in the solar system. And one of the most interesting commodities that we think are out there is water. What the concept is Bennu, if it is related to our carbonaceous chondrite meteorites, most likely the material experienced hydrothermal alteration very early in solar system history. And that hot water basically reacted with the rocky material and created clay minerals. And clays have water bound up in the crystal structure. And so the idea is that if you have a clay-rich asteroid, you can process that material basically by heating it up, driving the water vapor off, and then separating the water molecule into hydrogen and oxygen, which is a very powerful rocket propellant, and then basically establishing fuel depots across the solar system to further human and robotic exploration. So our interest and my interest in it scientifically is that, first of all of the amazing work that Mike Moreau and his team are going to do flying the spacecraft around the asteroid, and Sandy, a friend, and her team at Lockheed Martin in controlling the vehicle, these are first-time events in spaceflight. This is a challenging environment. Precision navigation of the vehicle in the microgravity situation around Bennu is groundbreaking. Any asteroid mining endeavor is going to have to understand how to do that, and the techniques that we're developing are going to directly translate to that as well. And then finally, we're bringing material back. One of the key areas of interest is the water content and the organic content. Those are prime commodities for asteroid mining, so we'll establish if Bennu indeed is a viable target for that kind of operation in the future.
Thank you very much.
Thank you. Our next question comes from Emily with the Planetary Society. Your line is open.
Hi, it's Emily Lakdawalla with the Planetary Society. I know that the OSIRIS-REx mission is working very closely with the Hayabusa 2 team. I'm wondering, now that the Hayabusa 2 has started doing proximity operations, if you, on your mission, have learned anything that will change the way you plan to operate at Bennu.
Hi, Emily. This is Dante. I just, in fact, got back from a trip to Japan. I was at the Institute for Space and Astronautical Science of the Japanese Aerospace Exploration Agency as they held their first landing site selection decision meeting. So I want to thank our colleagues at JAXA for inviting me to participate in that. It was a great honor to be able to understand what they've learned about asteroid Yugu and how they're going through their site selection process. Some of the things that we've learned I alluded to earlier, particularly the validity of that spinning top shape that we inferred from the radar data from Bennu. That's good news for us, and also a fascinating scientific topic. We didn't expect Yugu to have that shape because it's spinning much more slowly than Bennu, and we thought that that was due to rapid rotation and material migrating to the equator. So either the rotation rate of Yugu has slowed down since the ridge formed, or some other phenomena is responsible for establishing that shape. We did see the surface of Yugu to be very rugged and bouldery, and that is causing some consternation among the Hayabusa 2 team in terms of where they're going to select their site. It remains to be seen whether we'll face a similar challenge. Certainly, I was able to work with the team to discuss some of the areas that we have worked on and how we're doing a safety assessment of the asteroid surface, looking at the slopes and the tilts and worrying about boulder contact and spacecraft tip-over rates, and I expect that that kind of collaboration will continue well into the future. Most exciting and important from my perspective is Hayabusa 2's mission timeline has them interacting with the asteroid surface much sooner than we plan to. Our nominal sampling is scheduled for July of 2020, and Hayabusa 2 will be deploying the DLR and CNES, both the German and French space agencies respectively, mascot lander onto the surface and getting direct measurements of the material properties and thermal conductivity and composition. That's invaluable knowledge for OSIRIS-REx because one of the biggest uncertainties we have is how does the material behave on the surface of the asteroid in the microgravity environment. So we are looking forward to that data, and the team is very open to sharing that information with us. And then, of course, nominally, Hayabusa 2 was planning on a first sampling attempt in October. As we learned at their press conference yesterday, they may be, they're going to do some descent operations and make an assessment about when they want to try that. But all of the information about the Hayabusa 2 spacecraft interaction with the asteroid surface will also be important for OSIRIS-REx as we design the final touch-and-go maneuver for our mission.
Thank you.
Hi, it's Nancy. I'm going to switch over to social media. We have a couple of social media questions. So Kimberly on Twitter asks, any predictions of what kinds of minerals Bennu will offer?
I'll take this one, Nancy. Great question. We do believe Bennu is similar to hydrated carbonaceous chondrite meteorites. That was one of the primary reasons it was chosen as the scientific target. So as a result, it may have some rocky material that's consistent with formation in the protoplanetary disk, that is the giant disk of gas and dust that surrounded the early sun and from which all the planets and the residual asteroids formed inside of. And there you get minerals that form actually in high temperature kind of magma environments as little drops of fiery rain. We call these things chondrules. And they're made out of minerals like olivine, which you may be more familiar with as the gemstone peridot, and a related mineral called pyroxene. We see metals, primarily iron and nickel, sulfide minerals where the iron reacts with sulfur to form something like pyrite, but different because of the unique chemistry in that early solar system environment, and it's called troilite. So that would be kind of if nothing had happened on the asteroid after accretion into the body. But we think that some ice got into there as well, and that ice probably melted and reacted with some of that material, and you would form these clay minerals that I referred to earlier. You may form things like carbonates, which you might see forming, in your kitchen sink if you've got hard water and it leaves those white deposits behind. Sulfate minerals, where the sulfides would also react with water and incorporate some of that water into their crystal structure as well. So it may be a combination of those. It may be a one extreme or the other. And we'll start to learn about the mineralogy when both the OVIRS and OTIS spectrometers start collecting data late in the approach phase and then getting an initial resolved look during those preliminary survey flybys. And, of course, OSIRIS-REx is a sample return mission, and exactly what we want to do right away when the samples are back on Earth is start characterizing the mineral abundances in that material.
Okay, thank you, Dante. I have another question from Jacob and Mike on Twitter. They both asked, how will OSIRIS-REx keep its sample safe during re-entry into Earth's atmosphere?
Sandy, do you want to take that one?
Yeah, I can take that one. The sample return capsule does have a heat shield that will keep the sample safe during re-entry. It's a similar design to what was used on the Stardust spacecraft that successfully brought samples of Comet Build 2 back to Earth back in 2006.
Okay, operator, we're ready to take, I think we have time for about one more media question.
Thank you. Our next question comes from Stephen Clark with Spaceflight Now. Your line is open.
Hi, thanks for taking my call. I think my question is probably for Sandy. You talked a little bit about the TAGSAM checkouts planned in the October timeframe. Is this the first time TAGSAM will be exercised since the launch? And can you walk through that process in a little more detail? For example, the launch cover jettison, is that a door or is that something that is jettisoned from the spacecraft? And just walk us through what you'll be looking for during that checkout, please.
Yeah, so you are correct in that later this year that will be the first time that we perform any TAGSAM operations since launch. So what that sequence of events looks like is we do need to jettison that launch cover. It is about a 1 kilogram cover that is sitting over the sampler head right now. So we will eject that, and then we will release the TAGSAM arm. It is also being restrained against the body of the spacecraft. Once we have confirmed those events, we will be free to move the arm around. We will get it up above the payload deck so we can utilize our cameras that are sitting up there to take images, show us that it is functioning as expected, and then we will go park the TAGSAM arm back in the launch container in the similar configuration that it is in now, and it will stay there while we do a majority of our proximity operations. Does that answer your question?
It does. Thank you.
Operator, I have an email. So for the panelists, I have an email question here. How soon will the site selection for the sample begin? What's the process look like?
I'll take this one, Nancy. This is Dante. That's a great question. If you remember from my first timeline graphic, we actually have 3 major campaigns identified in the mission timeline. The first campaign that we just started on August 17th is the navigation campaign, and then following that is the site selection campaign. So the navigation campaign is really for Mike and his team and Sandy and her team to learn how to fly, make that transition to landmark tracking optical navigation. We will get a first look at Bennu from the science instruments, and we're particularly excited about the late approach data and the preliminary survey. We'll be getting resolved information. And site selection will start at that point in the sense that we'll be characterizing the surface, understanding are we looking at something that's covered with boulders like Ryugu, or are there of particular interest to us patches of gravel or ponded regolith like we saw on the Itokawa asteroid, which was the target of the first Hayabusa mission in a region that they named the Muses Sea. But really, after the orbital A phase is complete, we go into detailed survey, and that is where the science really takes the lead. And we'll be first going through a phase we call the baseball diamond, so named because when we originally designed it, it had 4 observing stations, kind of like the bases on a baseball field, to get a wide variety of look angles and do stereo imaging and getting the right range of shadows and angles of observation. It still kind of looks like that, but we've refined the design of that phase since launch based on our knowledge of the spacecraft performance and as well as a better understanding of our imaging requirements. And then following baseball diamond, we go into the equatorial stations where we'll move around the asteroid along the equator at 7 different what we call local solar times. So you can think of like noon is right when the sun is overhead, and then you've got 3 p.m., 6 p.m., 9 p.m., midnight, etc. We can't do midnight, but we can do a lot of other times, and that'll tell us how the temperature of the surface varies, as well as getting great spectral maps from OVIRS and OTIS to understand the mineral composition on the surface. And that's really when the site selection campaign formally kicks off. and we'll be doing an assessment in 4 different areas. We look at deliverability, can we get the spacecraft where we want? Safety, is it safe for the spacecraft to touch down there? Sampleability, do we believe TAGSAM will collect material from that location? And science value, does the material have the best opportunity to answer our questions about the origin of volatile and organic material from the early solar system?
Okay, thank you. I believe, operator, that's all the time we have for media questions. So I want to thank you, operator, and I want to just let the people know that we have graphics from today's briefing, and it can be found at https://svs.gsfc.nasa.gov/13012. Thank you to our panelists and everyone for calling in. This concludes today's OSIRIS-REx Media Telecon. Thank you.